Before starting, let me just not clarify, but be a little bit more specific. So I am the software and our proposal that I am going to present today started few years ago as a research project between BSc and Lenovo in the context of energy runtime, energy monitoring and optimization, mostly for HPC at that moment, like 6-7 years ago. Okay, I'm still associate researcher and the team leader of the system software for energy management. And then like 5 years ago, we decided to create the ER company, which is a spin-off of BSc and UPC. And then right now, and this is just to give you a little bit more of context, we have decided that there's this, let's say, these two lines in parallel where at BSc we deploy what we call the ER core, which is the open source part of ER with the main functionality, both in terms of monitoring and optimization. But then we created this company to provide professional services on top of ER. And in the last 2 years, we also started some like private developments specific for the company, most in the context of GPU optimization, analytics, and so on. Today, the presentation will be a technical presentation. I mean, I am not going to enter into business details or these kind of things. Okay. So this is how I let's say, prepare this presentation. So probably the initial 5 minutes will be something that all of you will be aware or well known of why energy efficiency is needed in data centers, but I will give you a little bit our view of why it's needed, which are the stakeholders or the participant of this overall goal of having energy efficiency data centers, and where is the ER contribution in this global picture? Because of course we are a system software tool, and then we cannot have too much influence, let's say, for example, in the hardware or in other parts of the system like the cooling, no? But it's just to put the global context. So based on this initial motivation, I will go through different topics. What is our view of what is the full picture of the data center monitoring and management? In some of these parts, I will mention that we are doing some active development or active contributions, or at BSc or in the context of the company. And in some other cases, it's just the roadmap we have for a medium term, no? But this maybe in some of the cases we don't have yet any, let's say, or some solutions for some of the topics. Then I will give you some information, technical information about the way we implement and we offer the dynamic energy optimization. Then one of the features of ER, which is, I would say, one of the differences probably with other solutions, is that we also support complex scenarios like the not sharing for big servers, few details on the power cap, and then at the end, and I will not spend more than 1 minute here, I have included at the end of the presentation some useful links to the ER repository, ER documentation, and so on. So you will have an easy access to that. Okay. This is basically some kind of summary, and it's not a summary, and the real numbers are not really important because these numbers are changing again and again. No, maybe at the moment I got these statistics of these numbers, like I think it was like 2 months ago we were having this number. Maybe today is different, and in 1 month it will be even more. But it's well known. I'm 100% sure it's well known for all of you that the difference between the power or energy or power anyway that's available from the power grid compared with the power consumption of some data centers and the total power consumption is growing again and again. And what is even more relevant is maybe these two bullets. And again, you can ignore the absolute values. The important thing is the idea is that this difference between the available power and the power requirement is growing again and again. And then if we have in the new data centers, in the new application developments, in the new hardware, in all these actors I will mention later, we have this eco mine or green mine or energy efficiency mine or whatever term you want to use, we will still have some percentage of difference between the requirements, no, the increment in the power consumption and the availability. So there is a gap that is increasing, but is it even, of course, is even worse if in some of these actors, in some of these elements contributing to an energy efficient data centers, there is not effort and research and investment and so on to try to even increase this energy efficiency awareness respect to the increment in the requirements. Okay. So in some of the panels I have been participating in some of the discussion, no, sometimes it seems that it's only a matter of money. No, it's not. I think it's not, and I hope you will agree. It's not only, and we cannot wait that the market itself will, let's say, regulate what is efficient or not, because it's not efficiency like economically efficient. And also, if we look at that from a global point of view, maybe something that is efficient, if we look at our internal metrics, like for example in Europe, no, what we can consider is something efficient, but maybe we are using resources even from other countries, no? Or it seems that we are happy if we use our green resources, but maybe these green resources mean that in other parts of, even in the same country, they are not green, no? Can we, something that there was also some discussions in some panels, no? Can we avoid, or can we educate, let's say, people to not use so much for example, AI, no? I think the answer is not. I mean, a few months ago, I was thinking like, well, maybe, but it's very difficult. Honestly, this is my personal opinion, but I think it's something we cannot control. We cannot avoid people using AI for business and for things that are not business, no? For everything mostly, no? I am also using AI for my day-to-day work, okay? So what can we do? So what we can do is our best. I mean, being as much energy efficiency as possible, okay? So what are the metrics for energy efficiency on the different actors contributing to this global goal in a data center, no? So in my opinion, and I think this is what I think it's including everything. On one side, we have hardware vendors in that case, the data center itself. So applications, including applications here, I include application developers and application users, because it's the two sides of the same history. One is the development of the application, but then when you use the application, you need to use in an efficient way. And then there are all the, let's say, ecosystem of system software tools, runtimes, and so on, where probably ER is included, no, in this box here. So for a hardware vendor, they are mostly focusing, if you look at the top 500 or green 500, so it could be only flops, only performance, or in the best case, gigaflops per batch, trying to get the maximum number of flops per power, no? If we focus on the data center, so the metrics are the PUE or the carbon intensity or the CO2 consumption, okay? If we go to the application developers or final users, in most of the cases, they only care about the time to solution. And I will come back here because something we need to, let's say, probably have a global discussion, at least in Europe, is in the way we are accounting the utilization of the HPC and AI resources. No? But this is a discussion that, of course, is completely out of the scope of this call and even the capability we have to have a real influence, maybe. No, well, I don't know if we can influence or not. And then on the system software, probably the metric that the HPC data centers or AI data centers, and this is related with the applications, is what they mostly care is about the throughput. Okay, so one of the concerns about power and energy is that if in case we try and we are really try to optimize, even if we are an application, a developer, an application user, and so on, is that it's very really difficult to get these metrics, or at least till now it's very difficult because there was not a standard tool or mostly a standard tool. There was some different libraries providing sometimes from some hardware monitors or from, for example, for Rappel, or depending on the data center, there was the possibility to get some metrics, but there was no standard tools, not at the system level, not an homogeneous criteria, even from what is energy efficiency or what is not. And then that was generating that there is not too much expertise on application developers, on sysadmins, on the technical support team for HPC data centers. So in my experience, in case of ER, we have installed ER in several data centers. And for me, it's 100% clear that the expertise, it's even not present, let's say, in the case of the sysadmins or the team providing the technical support to users. And that makes sense because till now it has been very, very difficult to get access to this information, mostly on the hardware side, no, for power or system monitoring, but not correlated with the application. And then there is not too much knowledge of what is the relationship between other performance metrics rather than only execution time, and then the power consumption, and then at the end, this metric with more semantic of energy efficiency, and also the different sources of power. So I have had a lot of meetings, conversations explaining to, for example, BSc users or other users from other data centers, the different sources of power just for comparison. When they want to compare what is the power consumption in the GPP partition in Mare Nostrum 5 compared with other cluster, it's very important they know the source of the power so they can compare, because if you compare node power with CPU power, it's not the same. So you can even not do a fair and, let's say, robust evaluation, no, about the impact on your application or on the optimizations or in your strategies or whatever. Okay, and of course, if we enter in the context of the new or maybe not so new use cases like virtualization, workflow, node sharing is very, very complex. And as I said, there is even not an agreement. Even there are 2 or 3 metrics that are, I would say, they are considered as mostly a standard on energy efficiency, like the gigaflops per watt, but there is not really an agreement on what is exactly the metric for energy efficiency. Okay. So if we go to system software tools for energy efficiency or to generate the energy efficiency data center, okay, so the goal of these tools, and this is where ER fits, is to help application developers and also the sysadmins and the technical support team to get the optimal configuration, both static and dynamic. Okay, so in static optimization, the main effort has been focused on this part in optimizing the resource utilization. And what is true that having an efficient resource selection, resource utilization is key for an energy efficient data center. It's really, really important. If you reduce the execution time, automatically you will reduce the energy. Okay. But then, of course, there are some additional settings like playing with the BFS or something like that you can contribute with an extra, like an added improvement on the static, from the point of view of the static optimization, which is completely complementary to dynamic optimization, which again, you can apply some techniques for resource optimization, power, frequency, and then energy, okay? Or you can play directly with energy, but at the end of the day, it's mostly the same, okay? What are the, let's say, the challenges for the different stakeholders, in that case, the participants, in looking more from a human point of view, no? So in a data center, we have users, we have admins, and then what we can say, the data center management team or the data center owners, no? So they have different perspectives and they have different goals. So I will correlate this comment, let's say, or these bullets with our contributions and our roadmaps. So from the point of view of users, the main motivation they have is to have more scientific results, okay? So they have not too much expertise. So many of them, they are even not computer science, of course. No, they are physics or whatever, chemics, or even from business, from economics or whatever. So they don't have any background on HPC or in computer science, and it's very difficult they have, and they don't want to have, because the only thing they want to do is to get more results with the same resources. So it has to be easy and transparent, okay? But for some of them, they have some knowledge. There is still some challenge in helping them and make it easy, because even for computer science or people with some expertise, it's not really easy to understand and to get this conclusion of, if you get these metrics, maybe you have to do that, or you can do that to be more energy efficiency. For the sysadmin, the main motivation, or one of the main motivation, maybe there are others, of course, is to keep the system running and operational under the limits. Limits could be the number of nodes, could be the number, the maximum power, whatever limits, and of course, up and running the system, being more robust and increasing the reliability. Okay, so for the admins or the technical support team, it's also very, very important to be as much automatic as possible. As much automatic means that it has to be ideally transparent for users, so they are not receiving mails asking or claiming, mails with questions or mails with claiming about the tools or the software, and then offer some features like automatic configuration and the automatic management, or in particular, what refers to here is about power or energy. Then there are, of course, the other tools like the scheduler and so on, but this is out of our context, okay? And from the point of view of the data center managers or the data center owners, they are more focused on maybe on economical things, no? So they have to maintain the system with in that case, the economical limits, the budget, the annual budget in power, energy, and of course, this is the electricity bill, okay? And then ideally using some tools, and this is one of the lines that we have open in the company part, in the private part, some analytics tools to help to improve the configuration of the system, improve in our case, improving in terms of resource utilization, and then the configuration of the different optimization policies and so on. Okay, so this is one of the lines I will not enter today because we don't have enough time, but this is one of the lines that we are working on the company, trying to provide these hints automatically, for the individual users, but also for the data center managers. Okay, so as you see, the main conclusion is our main conclusion also at the beginning of the project, it has to be easy. And that was also based on the experience of a previous tool, not tool, but a previous strategy applied in some data centers in Germany, that they were doing some energy optimization based on some user schemes. It demonstrated that relying on the user feedback or relying on the user provided information, from the point of view of the data center, this is not robust. So one of the first premises for ER, it has to be not only easy, but it has to be automatic, the two things. So no input from users, and ideally 100% transparent. Okay. So what we will try to do is if we are focused on this part, we will try to provide the optimal settings for the data centers owners to improve the configuration, to select the optimal optimization, or the best, the best configuration, the best optimization policy with the best threshold according to the workload executed in the customer or in the data center, okay, in any way. So the hardware configuration, we will have to set also the best dynamic settings in terms of CPU frequency, GPU frequency, memory frequency to run in the maximum performance per watt in the data center limit, okay? With our tools and with the hints, this is in this other side. The applications will run in this optimal configuration, and then the main contributions is in this part, is to get the optimal both runtime and static configuration settings to optimize on runtime, and then also, as I said, to inform both users, sysadmins and the data center managers to have an influence and improve statically, so it's complementary to the dynamic optimizations. So the basis of our solution is a powerful monitoring. Powerful monitoring into, let's say, from 2 points of view. On one side, more hardware is data center monitoring, and on the other side, with much more semantic, is application monitoring. An application is different from job monitoring, because in the particular case of ER, we are able to identify the different, let's say, elements, but I assume if I say application, you understand that potentially are part of a single job. So we can have one job with one application, or there can be one job of one step, with one application or with multiple applications. And then these applications can be independent, or they can be with some dependencies. And in that case, we can think in a workflow. Okay, so that's the main difference, at least for us. So the main requirement in terms of the data center monitor, and this is not a requirement for us, this is the requirement we have when we analyze a data center. And this is, for example, we are participating in the Synergy project, in the Synergy European project, and one of the things we are discussing right now is the monitoring infrastructure. And it's clear there are all these requirements. So depending on the data center, they want to compute only, or they want to monitor computational. Typically, it's an non-computational devices, or storage, network, and so on. There is really different requirements in terms of granularity. So in some data centers, they want to monitor, surprisingly, with a frequency of milliseconds. So honestly, I don't know if this high frequency is really useful, but in some data centers, they want to have this really, really fine grain. But in others, they are a little bit, I would say, more realistic, and they go to hours. I think in the middle is what is more reasonable, but of course, each data center, they take their own decisions, okay? And then, of course, there are different sources of data, in band, out of band. There are some tools already doing some exports of information, operating system metrics, per process metrics. And then, of course, there are some different scales, from few nodes, like small clusters. Even right now with GPUs, we have clusters with few nodes, but being really, really power hungry clusters. And then, of course, very, very big data centers with thousands of nodes. Okay. In application, it mostly the complexity applies similar to the different bullets you have seen, but also with some additional complexities. No, like there are of course some devices, there are different programming languages, frameworks, schedulers, of course, the context of virtualization. So it start being really, really complex to support all these different angles in a single tool. And in terms of optimization, the only thing I want to mention, no need to go to all the details, is that optimization, depending on the scale that we are addressing, there are different strategies. So in some cases, people have what is having in mind is optimizing in run versus idle, and then maybe what you can play here is selecting the best CPU governor. As you see in my comment, as far as I know, there is nothing like governors on the GPU. I think it's not. What you have in Ball is the runtime optimization that we do in ER. It's while the application is running, so then only applies to run context, is the selection of the dynamic setting of always, in our case, we focus always on playing with the frequency. There are other solutions that play with power, for example, but we focus on playing with CPU, memory, and GPU frequency. You can also play with the governor. In here, we focus on the CPU, in fact, in the CPU and the GPU frequency. We also support memory frequency optimization. But this is from a technical point of view, this is a little bit more tricky because in some cases there are some collateral effects. And even if in the presentation, probably you will see that I mentioned CPU and memory, our optimization policies, they are focusing on CPU and GPU. And then there are other possibilities that we have started to explore in some of the European projects that we are participating, like synergies, and in the context of the company in the Odyssey project, trying to optimize when you run a workflow, okay? Because when you have some dependencies, I guess, or we expect that there will be some other new opportunities, no? If you analyze the diagram, the state diagram that describe our workflow, we can expect some additional opportunities taking into account which of these elements are in the critical path or not, or these kind of ideas, okay? And then something that we are in an exploratory part is the power, thermal, and cooling, power not, but cooling management. In that case, we are also participating in another European project called Diamond, which is one of these Pathfinder projects. And then in this project, we are exploring the possibility on doing some dynamic cooling management on the data center. But this part, of course, is a little bit more complex because we enter into the more hardware part, and then some collaboration with the cooling vendors is needed, no, to really be able to do some real or to have a real impact on this part. Okay, so let me go to some technical details. This is mostly what I have commented. So what we want to contribute to the final users is to be easy, and something that is very important, it's portable. Why is portable? It's important because if a final user has to do the effort to understand a tool like ER, even if the job submission is automatic, no? But if they want to do the effort to understand the additional tools included with the software to statically optimize their application, and then going to a different data center, or even partners participating in the same project, there are different tools in the different data center, that makes really complex to reach that point that you become not a standard, but something close to a standard that you can run in data center A, B, and C. No, so even if ER is not fully installed, it can be partially used, and then or a given user going from one data center to another, or for example, different users participating in the same project, they can use the same tool. And use the same tool means that the name of the metrics is the same in all the data centers, that the visualization tools are the same, that the CSV files, for example, that we generate, or the information we got from the database is all the same. And this is really, really important, no? Because as I said, the expertise in this part is not really high, no? So it's very important to be sure that the effort is worth to do it, okay? From the point of view of the admins, what we try to do on our side is the three topics you see here. So it's a new tool, so we understand that for the sysadmin, they are a little bit redundant to accept in some way, okay? But what we try to do is to do it in a very similar way, in particular to Sloan. So, of course, it's not the same, but the architecture is similar. The name of the commands is not so different, and the type, the flags, and so on. So we tried also to make it easy for them, and also to minimize as much as possible the number of dependencies. So installing or what is the basic make install is, I would say, easy. Okay, then the configuration file and so on is another story, but at least the installation is easy. Okay, and then something also very important is that it's really powerful for heterogeneous systems. So with a single configuration, we have here running in customers, for example, with 4 different partition types, with 3 different types of CPUs, 2 different types of GPUs, and there is a single installation and a single configuration file. And I think this is really, in fact, we comment that with some sysadmins, you see in the faces that they are really happy that there are no need to have 4 different installations with 4 different configurations and so on. So the data center management, as I have commented, it's one of the things we have in our roadmap, but we are not, it's still a work in progress part. Okay. So these are the features that we offer. As you see, and I have already said, in the center, there is this data center, but in that case, data center includes application. We use this collected information for everything, for accounting, for the runtime and post-mortem analysis with the tools, at runtime with our runtime library, and post-mortem with our tools. CPU and GPU optimization use these metrics, application metrics in particular, and this information is also used as the input for the smart power cap strategy that we also offer. Okay. Few details on what are we providing right now in terms of data center monitoring at the rack, node, and then application level. At the data center monitoring, I will show you later in the ER architecture, we have a new component. We call it data center monitor, but in fact, it's data center monitor and management. This component is extensible and plugin-based service, really, really flexible. Basically, the data center monitor by itself, I would say, is doing nothing. It's depending on the plugins. And right now, it offers some functionalities, some plugins for the AC power for, it can be used for compute nodes, but it was mostly designed to contact not computational nodes, because in computational nodes, we have a specific service for that. So mostly storage, network. So in the configuration, you can specify the list of sensors and the list of the PDUs, IPs that you want to connect. This information can be or is reported to the database. You will see in different slices that this reporting, I will mention that is very, very flexible. This is because the reporting in ER is also based on a pluggable system where we can replace one plugin by another. We have a generic API, and then we can use one or the other. So, for example, in general, when we install ER in a customer, we use MariaDB plugin. So we have an SQL database, but it could be Postgres, it could be CSV files, it could be log files, it could be Prometheus, for example. So just replacing one with the other. No? So the reporting is, of course, not 100% generic, but it's very, very flexible. Okay. Then we have some visualization based on Grafana. Okay. And then the integration of this monitoring of this storage, network, cooling devices, and so on with the full data center power cap is also a work in progress. We are extending the current service, which is only taking into account the computational service, to take into account also these other parts, which in most of the data centers is considered like mostly static or fixed, let's say, power consumption, but it's not 100% static. No, so to avoid having some peaks problems or problems from time to time, depending on these small variations, we have in mind to include the power of these other elements also in the system power cap. At the node level, as I say, we have a specific service for that. Of course, from a semantic point of view, it's considered as part of the data center monitoring, and this is what you have in this figure, but there is a specific service. Okay. So again, it's based on these 3 ideas: monitoring, report, and also these anomaly detections. Okay. In this previous slide, I didn't mention, but there is also some preliminary effort on this anomaly detection, and mostly about power on this storage, network, and cooling devices. So it's a service mostly focusing on power metrics and power related metrics like not power, CPU power, GPU power, but also CPU frequency, temperatures, or all these type of metrics associated, or from a semantic point of view, we can associate with power. So it's not only power, it's other metrics that gives additional information to only the node power consumption. So for example, we have the detail of not only the node power, but also the different devices in the node, the CPU, its socket, and the GPU, for example, and the memory, what is the power consumption for the different elements in a given node. Since the monitoring is very important for us, and I have a slide about that, we have implemented it in 2 layers, one generic and one specific, probably as many other tools, okay? But the good thing of this approach is that allows to maintain, let's say, a portable, maybe 95% of the code of this service. And then when we have to go to a new CPU, new GPU, or whatever, we only have to do the specific deployment, maybe for this model of CPU or this new model of GPU or whatever. But the core part of the service is 99% the same, okay? So we can support, for example, reading power or energy through IPMI, for example, in-band. Also, we support refis. For GPUs, we support NVIDIA and, for example, Intel Ponte Vecchio. We also have one installation with here. So different sources without having really different sources of our code, no? Just changing the specific part. The report is what I have already commented. And then as anomalies, we support power and temperature in the configuration file. For each CPU type, for each type of node, it can be specified different limits, okay? Like maximum power or maximum temperature, and in case there is a record or a measurement out of range, then we send an event to the database, so it can be tracked by these additional tools tracking the events on the database. And at the level of the application, the main thing to remark is that it's 100% dynamic, and there is no need of code modification. So here intercepts the execution of the application automatically. So depending on the type of application, we use one strategy or another. For example, for MPI applications, we intercept the MPI calls through the PMPI as other tools. For no MPI applications, we intercept the constructor and the destructor of the application, and we do some monitoring periodically. So the set of power and performance metrics that are characterizing the real activity of the application is what we call the application or the runtime signature. Okay, so this signature is really a characterization of the activity. So it's what my application is doing. Is using the CPU, doing what, are we generating some flops or not, CPU utilization or not, input output, MPI. So we collect all these metrics, so we know without any user intervention or without any user hint what the application is doing at any moment. So here you have a schema of a generic, it's completely a generic data center with the different services or the different components that ER is installing in a given data center. So each one of these columns represents one of computational node, okay, with CPU, GPUs, maybe some others only with CPU. That's not relevant. We support both. So we have this ER daemon running on, it's a Linux service running with root privilege per compute node. Then, of course, we will have, let's assume you have the application. The ER library is the component. It's a shared object, which is loaded together with the application, and it's implemented this application monitoring, having the semantic, no, the application signature and the runtime signature. And the ER library is the one also applying the optimization policy. And since changing the CPU or GPU frequency requires privilege, the ER library relies on the ER daemon running on the node to apply these modifications. This ER plugin depends on the scheduler. So we have a plugin for Slurm, one for PBS, for example, and it's the component that notifies the ER daemon when there is a new job, a new step, a new task. So all these events. And this is the only element, this is the only part on ER that really depends on the scheduler, and it's only the API, so it's a really, really minor dependency. Data center monitor is the component I have commented that we are, let's say, increasing the utilization on the ER project, but because it's very configurable, so it can be present or not depending on the metrics we want to monitor. So, for example, if metrics collected by the ER daemon are enough, there is no need to run a data center monitor. But in the picture I have included for, let's say, for the completeness of the figure. Then from a software point of view, in the configuration file, we group computational nodes in Iceland. We use this terminology that comes mostly from the first customer at LRZ that we have. It's completely software, so it could be any grouping. It could be one single Iceland, including the whole cluster, or it could be, I don't know, whatever. It could be a partition in the coming from a Slurm or whatever. Again, this data center monitor per Iceland is optional. It depends on the requirements. And these two elements are the database manager. So this element is the one that is, let's say, collecting all the data. Sorry, it will be more the blue arrow. Collecting all the data from the ER daemons on the Iceland and then minimizing the access to the database server. So we do some aggregation and minimizing the number of elements. And then the global manager is the system power manager. We are migrating to this more, let's say, not standard, but the terminology standard that we are trying to use in Synergy, in the Synergy project that also comes from the Regale project. I don't know if some of you were involved in this project, no? But it was an European project trying to generate an European software stack for power management. So we still name the services as the original names, but in some presentations, maybe you have seen the not the new names, but this more standard. Okay, so let me go to more the details. Otherwise, we will not have time for questions. So this is what we call the ER library optimization loop. The ER library, as I said, is a shared object. It's plug loaded with the applications. And then dynamically, these different stages are applied. So when you start, you submit your applications. We had one phase that we call loop detection, because if the application has some repetitive pattern, we have our own algorithm to identify this repetitive pattern. If there is not, we switch automatically to a time-guided mode, okay? Then we start computing the runtime signature, which is classifying the current activity. We compute these runtime signatures every approx 10 seconds. So it's not milliseconds or 1 second, it's 10 seconds, okay? So it's different granularity than other, let's say, other tools. So when this signature is computed, we classify what is my application doing now. So do we have some CPU activity, MPI activity, IO activity, GPU activity? Let's say these two classes are what we will refer as computational phases. So in case we have intensive MPI phase or intensive IO phase, then we will apply to, let's say, preselected CPU and GPU configurations, okay? But in the more generic case, like we are in a computational phase, then we have some CPU and GPU energy models. Then the policies based on the predictions provided by these models. What these models provide is, okay, these are your current metrics, and then the models predict what will be the execution time and the power if we change the CPU frequency or if we change the GPU frequency. So if you have these predictions, execution time and power, then applying the energy policy is just selecting the best configuration, and best configuration, of course, depends on the policy. So for example, the policy that we install with ER by default is a mean energy to solution, which is a policy that, of course, selects the configuration with the minimum energy, but we impose a maximum time penalty just to guarantee that in an HPC or AI environment, we are not penalizing the application too much. Even execution time is already included in the energy. We have, let's say, this second factor to guarantee that we are not increasing too much the execution time. And this is really, really interesting because the execution time can also have some impact on the scheduling. No? So it's important that there is an agreement with the data center on what is the maximum penalty we accept in an application. And then, of course, we set the frequency, we report the data so we can visualize, we can analyze, we can use for optimization. And this optimization loop is applied again and again during the life of the application. Something I have already commented, or I think I have already commented, it's important to differentiate between just utilization of the resources, like CPU utilization, of GPU utilization versus some effective utilization. And this is what the signature brings in here. The signature is having the semantic of what is really my application doing. It's not just using the CPU, for example, is the gigaflow per watt, for example, that we are generating. Or I am using the CPU to do what, to send messages, or to do what exactly. So it's not so important the fact that we are consuming power, is we are consuming power to do what. And this semantic of I am consuming this power to do this activity is that okay or not? No, so the policy, the criteria, optimization criteria of the policy is what tries to, let's say, to answer this question. It's okay, or should we change the setting, and then which settings I have to apply? Okay. So this is what I have commented before about the portability. So in that case, for example, you have an example of what can happen in terms of monitoring, for example, when the ER library is used with an application, and the case of management. In fact, the case of management and monitoring is exactly the same, but in most of the cases in management, all the requirements are, or all the actions, let's say, requires root privilege, and this is what they are in red. And then they have to go through the ER daemon, which is the ER node manager, and then the operating system. While in monitoring, it's much more frequent that there are a lot of metrics that you can access directly. So this API takes care of all these things. So for the ER library, it's transparent, and when we automatically detect if we can go directly and then be more efficient, or we need to go through the ER daemon API, for example, to get access to these privilege metrics. So this is what I commented in terms of dynamic optimization. Based on the signature, we apply the energy model. And what is relevant is that the energy model has these two inputs. On one side, the signature, and on the other side, these coefficients. These coefficients is a set of coefficients for our for the models, AR models. In most of the cases, they are regression models, okay? And then we compute the installation time. So these coefficients characterize what is the impact of some metrics on this particular application. So when we change the CPU, for example, or the GPU frequency, if the application has certain characteristics, we model what will be the effect, the impact on this architecture in time and in power. So then at runtime, what we have is, okay, so my application has these characteristics. This is what I got from the hardware. And then we can generate the execution time variation, the power variation, and then energy. And the energy means, of course, money. And then, as I said, the policy only has to select given some limits, like, for example, this threshold on the maximum performance penalty. So there is a core strategy, like minimize energy to solution, but slightly tuned with these thresholds that the policy accepts. Let me show you quickly some of the results we have on GPU optimization, which is one of the topics that we are working on the context of the company, but I think is relevant. No? So for example, in this graph, you have some results for the ER optimization for GPU, NVIDIA GPU, okay? In that case, it was so you have here, no, the detail, yeah, H100, NVIDIA H100. So different use cases. So these cases are AI, they are all TensorFlow with different models, okay? And then what you see here in this line is the frequency selected for each one of them. If I remember well, the maximum frequency for the GPU was 1.9 gigahertz, okay? And what you can see is the GPU power reduction, GPU energy, the performance per watt only on the GPU, okay? So what is very interesting is the results that we are, for example, having in this kind of context is that even more savings that on CPU only nodes, because of course that depends on the CPU model and the GPU model, okay? And of course depends on the architect, on the application of the use case that you are running, okay? But for example, with allowing a 5% of policy threshold, which means execution time impact, there was an energy savings in GPU saving again of 18 or around 20%, as you see. Okay, so it's really interesting. It's not really promising. It's interesting, no? These are exactly the same graph, and I will share with you the slides later, so you can look at them carefully if you want. But with 10%, if we allow up to 10%, and of course that depends on the data center, but then you also open the possibility to have up to 26% in average of energy saving. And something that is also worth to mention is that, of course, energy includes time penalty and power reduction. But if you see the column for power variation, it's very, very interesting, because if you have power-hungry use case like these AI use cases and you reduce 30% of power, of course, with some penalty, but 30% of power, that means that you have a 30% of extra power available to run other workloads. So in the case of power-limited clusters, energy optimization is relevant for the two things, from the two point of view. One, for the energy saving, but also for the power reduction. No? So it will have a positive impact on the throughput of the system. No? So energy has been, or energy optimization in most of the cases is visualized as a pain in performance, but we can imagine that in the future, it will be a benefit for the throughput of the system at the end, because the power will be consumed in the most energy efficient way. Okay. So this is the same, but for AgroMax. So it's an HPC use case. So there is no need to, let's say, to stop here. Okay. So you have some results. Few remarks. I'm sorry about that because I am consuming too much time. The node sharing support. So with taking into account the big CPU nodes that are in most of the GPU clusters, there are also some other strategies, like, for example, NVIDIA in the Grace Hopper, they have decided to put a single socket, no? But still there are a lot of data centers having very powerful, so it makes sense to share the nodes. Even if it's CPU only, it makes sense in a lot of cases, okay? So the use cases that we support are multiple applications that can be running, can be monitored and managed independently, okay? And also we support the case that multiple applications that are in the node with some environment variables here are considering them as a single entity. So we support some configurability of how we consider these different entities, like independently, and then optimizing each process or each application independently, or all of them together, and then reporting also as a single application, okay? So the way, there are no details in this presentation about how we implement the node sharing, but basically we also have some models. We are able to, let's say, split or distribute the metrics that are only available per node, or mostly per node or per socket, like the power or memory bandwidth. These per node or per socket metrics, based on the application signature, we have these models that we can estimate or split. The power of this application is X and the power of the other application is Y. So it's based on the application signature plus the real power consumption of the total node, okay? So in this example, for example, what you have here is the visualization of using one of the ER tools, the ER job visualizer, of one use case where we were running two PyTorch in the same node, okay? One of them with optimization and the other one without optimization, okay? So for example, this row here, this row here, and this row here are for the one of the PyTorch that was executed without optimization. And what you see is the application power with a gradient of color, where green means low values and dark blue means high value of the application power, GPU power, and the GPU frequency. So as you see, for example, in the case of the GPU power, so this one without optimization was consuming much more, of course, more power than the one without with optimization. And then this is the GPU frequency. So this one was running at the maximum. At the beginning, there was a period with less activity, but then the optimization was adapting the GPU frequency at runtime. So this is one of the use cases we show what is ER done in, what is the ER library doing at runtime, and how it works. This is exactly the same, but with a video. So if you don't mind, I will skip. And if you want to see, I can share with you. But it was exactly the same. So this element here was the GPU 0, GPU 1. It was with monitoring and with optimization. And in this graph, you see the GPU frequency and the GPU flops per watt. Okay, so it's a metric of the energy efficiency. So I will not play the video because it takes some time. But even if with the static image, you can see that the gigaflops per watt in that case, of course, is better, no? But that makes sense. Otherwise, I will not share this video with you, no? But it's a video that was showing at runtime, a plot generated at runtime with the metric that ER is collecting with the ER library. Okay. Very, very quickly, I will just comment on the idea of the smart power cap. So the key point for the smart power cap, maybe it's even better to show here, is that we have all this monitoring, so we can allocate and reallocate dynamically the power to the applications that are doing a better or a high energy efficient utilization of the resources they have. So different from other solutions that are only at the hardware level, what is different from here is that we have this collaboration between our elements, our components in the software. So the runtime library gets application signatures and runtime signatures, and in this signature we have the semantic of the requirements in terms of frequency, and the utilization. And utilization is not explicitly utilization, means activity of the application. So these two inputs are used as hints for the algorithms that we apply in the computational nodes and in the cluster. Okay, we have these three layers. On one side, the ER library, it's sharing or notifying about this semantic of what are my requirements and what is the utilization and my current activity. Then at the computational node, the ER daemon implements the distribution of the power between CPU and GPU, taking into account this information, and also report this information to the global manager, implementing the global reallocation. So if you maybe you don't remember, but from the from the slide I showed with the architecture, the global manager is also a hierarchical service, so there can be more than one. Okay, so that there can be a global view of the cluster, but also it can be done on different groups specified in the configuration file. Okay, so you have here an example about this, how the algorithm can work. So that would be the initial distribution, then having this application feedback, and then asking for the status, and then sending that redistribution. This is the main idea of the smart power cap. Okay, changing the dynamically. And I know we are on the limit. Sorry about that. But the only thing I would like to let's say emphasize again is that we are also doing some experiment with simulations at the cluster level, in particular evaluating this idea that I have mentioned, that in power limited scenarios, having some energy efficiency management, having this type of tools, this type of policy, in the short term, it's not going to see as a pain for the performance. It's going to see as a must if you want to get an optimal utilization of your system. So in this graph, what you can see is the increment or reduction on wait time and reduction on runtime and response time of a system, a cluster, using a solution, a smart solution as ER, compared with, for example, a static power cap. Okay, so it's not a penalty, it's an increment on the throughput of the system, but of course in power limited scenario. I hope you understand. Okay, it's not if you are free, you have free power and then you can consume as much as you want. Okay, sorry, I think the presentation I didn't compute enough the time, but you have some details here about the tools that they provide, about the accounting, visualization with Grafana, for example. Okay, but that was the last part. And then something I have already mentioned, the European projects where we are involved right now, Diamond, Odyssey. These two projects are with the company, with the Energy World Solutions, and these two projects are ongoing in the context of the BSc. Okay, and then at the end you have the links to the GitHub repository, which is a mirror of the BSc one, the wiki, which again is a mirror of the BSc one, and the link to our company in case you want to have some other publications and so on. For example, they are in I recommend you better the BSc company, because in the GitLab is not, the BSc one is not updated. So publications and so on are the one of the company. I am sorry about having consumed all the time. I think I have commented too many. Right. Sorry about that.
No problem. Thanks, Julita, for this talk. We have time for a few questions, of course. So for me, one main question is looking at how hardware prices have evolved in recent years, and energy prices have been soaring and then they're sort of down again. Now, if you compute how much power you draw over a year or so for an H100 GPU plus the necessary infrastructure, and then how much you paid for the hardware, for the total cost of ownership, the actual power cost it's not negligible, but it's of the order of 15 to 20% max. So if you save from that 15 to 20%, if you save 20% in energy with a minor penalty in performance, is it really worth it? Do you feel in your customer base that people are less inclined to look at energy optimization because energy is not the first class citizen of saving money?
Probably, yeah. I mean, there are like two problems. One is something I have briefly mentioned before, that from the point of view of the users, they don't care too much because what they get allocated are CPU hours. So users, they are not asking for that service on one side. And the other one is what you mentioned, probably for the data center, the total cost is not a big issue, no? And in most of the data centers, in particular public data centers, I think they don't pay directly the electricity bill, so or it's not really a pain for that to pay the electricity bill, so they are not too much concerned about that. My feeling is that this situation probably will happen where the money is not the problem, or it will be more problematic when you have real limitations on resources. As for example, I was saying at the end, these data centers that they are having more and more GPUs, and then probably they don't have enough power to run the whole system, the full frequency. So in that case, they will have money to have the hardware, but they will not have power to run the hardware they have. No, so if you use more efficiently the power that you are available, then you can take more benefit of the hardware that you are available in your system. And of course there are other limitations. No, for example, in the last year, I have received some mails from data centers where I have access that they have to switch off the system because there was some temperature issues because of the weather or something. So there are other elements that requires more a global management, not only power, no? So temperature, water consumption. So there are all these open topics that are not only money, no? So I agree with you. Maybe money is not a big issue because there is a lot of money, and also if you look in the AI context and so on, there is a lot of money to use. But some of the other resources at some point will be in the critical path, no? When there is no more power, no more water, or you cannot reach a certain temperature because then your system will be stopped and then you lose all the workload that you were already running, and then you are losing a lot of money. No, it's not only losing money, then the users claim, or maybe if you have some workflows running from companies or whatever, or you are a cloud company, you have to stop your system. This is a big issue for a data center, no?
Okay, no, the raised hand. Michael, speak up.
Yeah, hello. Thanks for the talk. And first of all, I think your software or the library is really cool, and I like the idea. What I wanted to ask is, from a user perspective of HPC software, is it also possible to use this library for monitoring within the software, that I can, for example, create like tags in my software for specific time measurements within a run? For example, there are software like Liquid, where I can measure specific peaks in frequency for performance, but I'm at least not aware if there is something existing for energy measurement or for metadata from the cluster.
We have a very simple API providing very few features for that, because that was a requirement long time ago for a customer, and then we created. It's not an API including all the metrics that we measure internally in the library, but it's true there are other libraries for profiling like Liquid or Puppy, as you say. So what we offer is the monitoring the power, the GPU power. Sorry, the not power, I think including the details like CPU and GPU, but I'm not 100% sure about that. But also the two basic functions to change the CPU frequency and the GPU frequency in case someone wants to do some like their own criteria to set the CPU frequency and the GPU frequency. That was not our goal, because as I said, our goal was to be 100% transparent. But we have this for this special case, we have this very, very simple API for power monitoring and then for setting the CPU and the GPU frequency. But it's like kind of research API. I mean, it's not something that people is using extensively, because in fact for users at the end, most of them, what they prefer to do it is just put AR on and do whatever you want, or AR off, no? But if they want to use or not use it, no? Probably in the Synergy project that we are participating, we will do some kind of API, because there are some tools, not final users, but tools like workflow managers, that they will require this type of API to take their automatic decisions, no? So it's from our point of view, it's like a final user, but in that case, it's another tool using our tool, no? So the API right now is quite simple, as I said, but I assume in this Synergy project we will extend a little bit and we will improve it.
Okay, thank you.
All right, Julita.
Thanks for the talk. I just was curious to understand your perspective about temperatures and power. So you said you use it to find or detect anomalies early on with temperatures and power. So I was curious to understand at what granularity do you capture the temperature data, like at node level or socket level or code level, and what do you use exactly to measure the temperature values?
So in temperature, what we measure is the CPU temperature. We also measure GPU temperature, but the anomaly detection is only on the CPU. Extending to GPU is pending. So we measure the CPU temperature, so per socket, and then what we do the only actions we do right now is we report a message in the logs of the log of the node, and then we send an event to the database that can be tracked by some of these other tools that there are for detecting notifications or detecting events on the database. And the limit is set by the sysadmin in our configuration file. So we can specify characteristics per type of node, like for example, the energy plugin for to read the energy of power, the limits on power, the limits on temperature, the coefficients files for the optimization policy. There are many parameters that can be specified. We call it tags, but it's like partitions or group of nodes. And then one of the things is the temperature limit.
Right, because
We are not taking actions. The only thing is reporting in the database that there is a problem or an issue with the temperature limit.
right. Are there any sensors on board which just reports the temperature, or you use any interface? Like I have tried using HWMons's file system interface to source temperature, but we are not sure if the temperature values are reliable. So is there any opinion about the reliable numbers on the temperature you capture?
Sorry, is there? Can you say again the question?
What's your opinion on the reliability of the temperature numbers that you try to capture? Like, have you tried really measuring them? Yeah.
About the quality.
Yeah.
So honestly, I cannot provide. I haven't compared the numbers that we got with a different source of information. So what we measure is the CPU power, CPU temperature. We use, for example, in Intel CPUs, we use Rappel for that. And for the GPU, we use the NVIDIA interface. But about the accuracy of that, the quality of that, to have an answer, we should be able to compare with some other sources of information, like with some external sensor or something. So what I can tell you is that they look coherent. They make sense related with power and with the activity. The variation makes sense, so it looks to be coherent. There are no errors in terms that they are zeros of out of range values. So the metrics make sense, but I don't know how accurate are really the metrics, because I have not compared with other sources of the data, which probably to have an answer to your question is what we should do, no? To have a different source of information and then see if it's good enough or not, no? So makes sense. They are robust enough in terms that they are not failing. There are no errors. Like, for example, node power is a metric that is failing very frequently, no? A lot of values out of range with very bad accuracy. And there is no need to compare, because you cannot be reporting like 10,000 bats when you run an application in a normal node. So it's clearly an out of range value, no? Or whatever, millions of zeros, and then or -1 or this crazy value. So there is no need to compare to know if the metric is accurate or not. But for temperature in particular, the metric makes sense, but I don't have any other source to refer to the accuracy of the metric itself.
At least in terms of power measurements, our friends from TU Dresden, they have a couple of publications where they compare actual power measured by different means, by a separate measurement device, and what Rappel reports. And then, well, they get different results depending on the CPU architecture. So there are some publications on that, at least for power. For temperature, I have no idea.
Yeah, for power, I have seen also in Rappel. I don't remember exactly. I think the conclusion was there was some inaccuracy. But if you compare, for example, with no power, they are excellent. So it always depends what is your limit on what is good and bad, no? But I remember for Rappel there was something and power. But again, temperature, I don't know. I have not an answer for that.